This lesson deals with spice parameters for a BJT. You can find these notes in the ECE302 ebook in Chapter 10, starting on page 10. Let's build a large signal model for the NPN transistor. We can do that by starting with the model we had previously, where we've got a diode between the base and the collector and a diode between the base and the emitter, and now we can add the forward and reverse bias capacitance associated with those diodes. We can add series resistors for the wires coming in from the collector, base, and the emitter, and also take into account the ohmic contact resistance we have between the wires and the semiconductor. I'll call these terminals collector prime, base prime, and emitter prime. We'll take our controlled source and we're going to add two more terms to the equation for that. And that's shown here. This is the equation we had previously from Chapter 3 for the large signal model for a BJT. And now we're going to take these two terms and subtract them from 1. That's the base collector voltage divided by a scalar, and the base emitter voltage divided by a scalar. I'll explain what these mean on the next page. There's also a resistor across each of these capacitors, like we had for the diode, whose value is very, very large. It's 1 over G min, and that's 10 to the 12th ohms, or a teraohm. I didn't show these to make the drawing a little bit simpler. We added a capacitance between the base and the emitter and the base and the collector. Associated with that diode, we have a reverse bias capacitance, or depletion capacitance. We also have a forward bias capacitance, or a diffusion capacitance. Between these two capacitors, we have a common terminal of a base. The term CJ0 we had for the diode, we're just going to put the letter E here because the base is common. This makes the subscripting a little bit easier. And likewise for the grading coefficient, we're just going to put the E subscript here, indicating that that's for the base emitter diode. And then for the built-in barrier potential, we'll do the same thing. We'll just put an E subscript with the 0 that's there. This is valid as long as the voltage is less than or equal to some constant. That's defaulted to 0.375, but you can change this, and in fact this is changed in most models. And then for the forward biasing capacitance, we'll have a transit time of minority carriers, but we'll put an F subscript associated with this diode, because normally we forward bias this diode when we're in the active region and reverse bias this diode. They use an F and an R subscript for that. Same is true for the eta. And then, of course, our voltage here is between the base and the emitter. What's added here is some more terms actually overlapping with this reverse bias capacitance, with the CJ0 term and the ME term and the VE0 term. This is going to add a small number to this one. It's going to improve the accuracy, but the bulk of the number is coming from here. And I'll show you that with a numerical example in the next video. Likewise, for the base collector diode, we have a C subscript here, a C subscript, a C subscript. And, of course, this is the base collector voltage across that diode. Same default value here. And likewise here we're going to have for the transit time of minority carriers, we use an R subscript. Likewise over here. And again adding this extra term with now a C subscript where I had an E before. And likewise over here and likewise over here. How about the large signal model for the PNP transistor? Well, in SPICE they do that by just changing the sign on all the equations. All the directions are the same in SPICE. They're not the ones that we're using in the course, but they're showing all the currents entering the transistor. And then for the model, same thing. All the currents are in the same direction as they were before, but now the diodes are reversed because the P and N material have been swapped out. Same equations we had, but now every current and every voltage has a change in sign. The same is true for the capacitance. And I've highlighted these with a little yellow marker, but you can see the change in sign associated with each of these variables from the previous page. Easy for a computer, hard for a person. If we do comparisons between our hand calculations and what SPICE is calculating, these are the equations that we're going to use. But remember the definitions of the voltages and currents associated with the transistor symbol that we showed on the previous page. Let's convert our notation to SPICE notation. So we had subscripted variables in Greek characters. But in the original SPICE program, they just had uppercase letters. I sub S is IS, default value is 0.1 femtoamps. Beta F is BF, default value of 100. Beta R is BR with a default value of 1. Eta F as NF with a default value of 1. Eta R, NR with a default value of 1. The voltage V sub AF is VAF with a default value of infinity. I'll explain this in just a second. V sub AR, VAR, default value of infinity. Series resistances for the base collector and the emitter. RB, RC, and RE, default values of 0. We can make a perfect transistor with no resistance associated with the wires or with the ohmic contacts. This is great for trying to figure out what's the best that you can ever do. You can find these terms in the Rashid reference text in Chapter 8. Continuing, we have the term C sub J E0 is CJE with a default value of 0 farads. V sub E0 is VJE, default value of 0.75 volts. M sub E is MJE with a default value of 0.33 dimensionless. Tau sub F is TF with a default value of 0. This is going to make the capacitances for reverse bias and forward bias 0. You can see what a perfect transistor could do, and then you can add these in and see what the effect of having capacitances in your circuit. Do the same thing for our base collector diode. So we have a CJC, VJC, and MJC, same default values. And lastly, tau sub R is TR with a default value of 0. We had the term VAF on the previous page in VAR. This is called the Early voltage, and it's named after James Early, who wrote a paper in 1952 where he found the curves had a slope to them as the voltage across the collector emitter increased. And what this did was also increase the amount of reverse biasing between the base and the collector. This created what's called a base width modulation effect. But the thing that he saw experimentally was that these lines all come to a focal point along the x-axis between the second and third quadrant. This is referred to as VAF in SPICE. VAF is actually a positive number, but it's shown here with a minus sign added to it. There's a similar definition for VAR when you're plotting curves in this third quadrant, and you have a slope associated with them, and they actually have a focal point here between the first and the fourth quadrant. What's shown here is a model for a 2N3904 NPN transistor that was included with the PSpice library in the student version. This is a transistor that we use in the ECE303 lab and is very common for hobbyists. The terms that we haven't talked about I've highlighted here in yellow, and the reason why there's so many of them is that between the base and the emitter there's actually 2 diodes, and between the base and the collector there's actually 2 diodes. This improves the modeling. Let's take the curve tracer circuit that we had in Chapter 3 and let's take this model and just test it. Now the new terms that are here, XTI, EG, XTB, model temperature effects. NE, ISE, NC, ISC, IKF, and IKR better model the currents in the transistor. FC models the transition for the capacitance between forward and reverse bias, and its value is multiplied by VJE or VJC, and that's where you're going to give that transition voltage. And then the terms ITF, VTF, and XTF better model the time domain behavior. Let's take a look at what the curves look like. If we were to plot the collector current versus the collector emitter voltage, and you can see quite dramatically things have changed, that the spacing between the lines now is not uniform. This is because of that second diode that's been added for each diode. We also have a set of curves in the third quadrant, and we'll take a look at those on the next page. Here I zoomed in on the third quadrant, and you can see the behavior here as we vary the base current from 0 to 1,000 microamps. And then I ran the simulation again, but now sweeping the voltage a lot larger, it's 40 volts to minus 100 volts. And you can see these curves have a tilt to them, and again it's called the early effect. But if you take these lines and extend them, they do come to a single focal point at minus 74 volts. And if you look in the model, the early voltage was 74 volts. And these are the SPICE parameters of a BJT.